Okay, so I know you can't see it right now, but we're going to look at something called the ideal gas law. Which the ideal gas law, by the way, should never be called a law, in my opinion. You want to know why?
Because it's ideal.
Why do I think this should not be called a law?
But it's not actually a law, it'd be ideal.
That's a great way to think about it. What did we know about laws in science?
They are proven,
Absolutely.
constant, and they have scientific evidence.
To be correct, how much of the
time.
all the time, 100%. This law is only true within a certain range of temperatures and pressures. This law does not work for extremely high pressures, nor does this law work
Too low.
for extremely low temperatures.
More like a guide.
Yeah, and this law makes some assumptions about molecules, which most of the time are okay. But we neglect some things that exist. So I don't think it should be called the ideal gas law, but an ideal gas would behave this way, and most gases do behave ideally under normal temperatures and normal pressures, the world we live in. Gases obey this law very nicely, but they don't obey this law all the time. So it shouldn't be a law.
Maybe other things don't obey it outside of the Earth.
Say that again?
You said the gases only obey on, like, for our Earth, with our temperatures and stuff, so how do we know everything else obeys?
Well, sometimes we need to do things at extremely high temperatures and pressures, and then they deviate from this law. So, here's what you need to know about the ideal gas law. The first one is it combines Boyle's law. Is there a place to write that down?
There's not the graph thing.
The graph things here?
No, it's not.
Oh, you might want to jot it down. So this law combines Boyle's law with Charles's law and who else? Avogadro's law into one great big ideal gas law. So all three of these combine to make da-dun-da-da, the ideal gas law. Keeping you up, are we, Devin?
Gas law.
Done? Can I move on?
No.
I gotta know. That means I can't move on. I can go down now? Okay, moving on. The ideal gas law is known as Prevnert. Prevnert. PV equals nRT. PV equals nRT. That's what you need to memorize. You can derive all the laws you need just simply by knowing Prevnert. 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 I know, there's not. It's called Prevnert. PV equals nRT. Prevnert. Prevnert. I don't know. All right, so let's take a look at the components of PV equals nRT. The first one is, if those things were true, what is the value of R? Go. I like to rearrange for R myself. That makes my life so much easier. And then I substitute my values in. And if you do that and you carry it out to the correct number of decimal points, that is the value of R. 0.08206, that is a number you must memorize. Are the units of R?
R.
Units for R.
R is.
It's the ideal gas law constant. So every time you use Prevnert, this number for R is the number you'll use for R.
So
It does have units. You need to pay close attention to the units. What else? So what's the unit of pressure? Atmospheres. What's the unit of volume? What's the volume unit for number of moles? Moles. What's the unit for T? Kelvin. Yeah, there's your units for R right there. Now, why is that important to know those units?
So you know which numbers are coming.
So you don't need to point off your test.
No, it's not about getting a point off your test. If the pressure is not given to you in atmospheres, can you use R?
No.
No. If the volume is not given to you in liters, can you use R?
You convert it.
If they give you grams, can you use R? If they give you degrees Celsius or degrees Fahrenheit, can you use R? No, but you can use it if you convert those so that they are the same units of R.
You can
Yes, there were some problems in your homework that asked you to do some simple conversions of pressure. They were some of the very first homework problems for this chapter. Yes, you must memorize that value. 0.08206.
I remember that.
And if you do your homework, man, it won't be any trouble at all to memorize that because you'll be using it. 0.08206. In fact, we'll do some practice problems today, and you might even have it before you walk out. Anyway, here's some assumptions that have made to make the ideal gas law possible. Later, I'll show you an equation that shows some corrections to the ideal gas law.
Sounds like you're not for this law.
Oh, I love this law. But you need to understand that we made some assumptions. The first assumption we make is that gas particles are so freaking small, the individual volumes of those atoms do not matter. Write that down, please. A second assumption, oh yeah, see how tiny they are? 0.1 nanometers. How many nanometers are in a meter? Anyone?
10 to the... No, that's way more than that.
10 to the 27.
Not that big. 10 to the what? Ninth. Because nano starts with an N, 9 starts with an N. That's how I memorize that, 10 to the ninth. In that collision, I don't know why that disappears. But it means that, when they collide, there's no loss of energy, which is... Last assumption is that there are no forces between the individual molecules. If they get close enough together, you and I both know there would be. However, for the ideal gas law, another assumption for this law, no attractive forces exist. And basically, this law works beautifully under ideal conditions of temperature and pressure.
Might as well you go with your time.
Then we'll have to use the van der Waals equation, which adds the adjustments in there.
So what happens if you use the Van der Waals equation for the ones that are normal?
You get the same answer. There'd be almost no deviation whatsoever between the two numbers.
So then they just use that one for all of them.
Because it's cumbersome, and this one's easy. They're all gone. Okay, fine.
So, what do you have?
Okay, so at what temperature? We're after temperature.
Yes, then you plug the moles into
Hold on a minute. It's easier than that. So I'm looking for a temperature final. So what would you want to call the 121? And I'm going to call that my initial volume. And what would I want to call this temperature? My initial temperature. And what do I want to call this? Pressure. Initial pressure. And what do you want to call the 293? Final what?
Final volume.
Volume. And what do I want to call this? Pressure final. Okay. What do I need to change out of these units? Yes. So this becomes what, 300 Kelvin? Well, actually, you don't need to change the volume, and I'll show you why in a second. Okay? All right. So all you need to know is Pervner. PV equals nRT. Out of those 1, 2, 3, 5 variables, which one of those will never, ever, ever, never change? R. So please rearrange this equation for R, please. This is a very important step. Oh, I better plug that in. Battery is critically low. Okay, better. So rearranging this for R, what did you get, please? R, and I'm going to call this initial, equals PV over NT. Initial, 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 initial. Well, if that's true for the initial statement, what would be true for a final statement? They'd be the same. So our final is equal to P final V final over N final T final, correct? Well, if these two are the same number, now what's true? Yes, I can set these two things equal to each other. So P1, V1 over N1, or I, is equal to P2, P final. You can use 2's if you want. I keep trying to. Oh, good. Now, any concerns or issues or problems?
Yeah,
Vanessa?
I remember when I took chem, there was. Are we always going to solve for R
Mm-hmm.
for those problems?
When you want to set them equal to each other, yes, you will always solve for R. 3 points, good question. Any other issues with this problem?
Do you know the number of moles?
Yes and no. Did the number of moles change in this equation?
It doesn't, so we can just
It
call
doesn't.
them
We can
one.
cancel them.
We can cancel them because they don't change. It becomes a constant. And they drop out of the problem. So you actually don't need that. But because it doesn't change, we know it's constant. Therefore, your final equation ends up with P1 V1 over T1 equals P final V final over T final. You have two choices at this point. You may put your numbers in and plug and chug, or you can do what Geek Me does, which is I solve for T final first and then plug my numbers in. I find it's easier, but a lot of students at this point do not find it easier. They'd rather play with real numbers than with variables. So if you'd rather plug your numbers in now and run the equation, that's fine. I'd rather solve for TF. And to solve for TF, I'm going to move this guy up there and move T initial here. So that gets rid of my denominators. And then to solve for T final, I have P final times V final times T initial divided by P1 V1. Questions on that step? I'll repeat the question. Why is it we could leave the volume in milliliters, but we had to change the temperature to Kelvin? It has to do with what's called a shift. And this is a shift by division. And you were absolutely right. When you said the ratio between the two is exactly the same. The ratio between 121 over 293 versus multiplying those both by a factor of 1,000 is the same. It doesn't affect the overall ratio. But when you have a shift of addition, that does affect the ratio. And that's why we had to change it. And it has to do with a shift. And when you get to pre-calc and calculus, you'll be looking at shifts in graphs and how to affect change in the shifts. And because the ratio remains, and that's the word I was looking for, but because the ratio remains the same, we didn't have to change them. Now, what if one of those was in milliliters and the other one was in liters?
Please, I know it's a lot of words.
Pick one and change it, yes. So everything just went away. That stinks. Did we say the negative 15 was 258?
Yeah.
And that the 36 was 309?
Yeah.
Oh, good, because I lost it when I hit the wrong button for some unknown reason. Okay, so handy dandy calculator. All right, I got 3.07. What's my unit, please? Liters. Does everybody agree with me?
That is 3.07.
Yes?
Yeah.
Yes? Did you get 307? Nice. Got it? Sweet.
You could.
Just about to ask you that, now that you were done writing. Okay, does anybody need help rearranging for V2? Quick and easy way. I like to rearrange for the variable I'm solving for and then plug my numbers in. A lot of students prefer to plug the numbers in
That's what I've been doing.
and then solve. Either way works. But I find the easy way to rearrange for V2 is I already know that V2 equals all of that. So that doesn't change. So I can easily go V2 equals P1 V1 over T1, correct? All right. And then I'm just going to flip these over. T2 is going to go on top. P2 is going to go down there. And then I plug my numbers in. Just another way to solve it.
You can't, but you can have a negative, see how I wrote it? You can have a negative change.
That is not right.
Okay, just click on
It's going down.
As long as you do change in volume.
It's going right in this thing.
Does that make sense?
I know, not something.
it. Discipline.
Man, the tools on this thing.
Oh, panel, there you go.
Yeah, look at that.
Look at that.
The other way around.
Now we can do this.
All right. I think we're all good now.
Oh yeah, by the time I figure out this.
You got it?
No, it's not. You know how much time I.
You checked mine?
You don't have the change in volume. It needs to be negative change because it decreases.
So it's a
your
negative,
changing volume is
negative 3.
negative 3. Yep. All right.
Wow. You got really far. And then I started figuring out.
How do you- Well, I'll hand it to you another time, Brennan.
You gotta look at the board.
Yes.
Not that board. You look at
Oh, I don't.
look at the board up there.
I look at the screen. Yeah.
She was on computer science.
Yeah, I do.
Oh.
It's all good. 61.
Oh, yes,